In this video, I will present an application of Rolle's theorem. It can help us answer the question, how many zeros does a function have? As a reminder, the main reason we have learned of Rolle's theorem is as an intermediate step to get to the mean value theorem. Nevertheless, it also has some other applications of its own, and this is one of them. First, let's make sure we use notation correctly. I say that the number c is a zero of a function f when f of c equals 0. In other words, we talk about a zero of the function f and a solution of the equation f of x equals 0. We never talk about a solution of a function. A function by itself is not an equation. Now that we have the right terminology, how do we find out the number of zeros of a function? A common strategy uses two steps. First, use the intermediate value theorem to prove that the function has at least a certain number of zeros. Second, use Rolle's theorem to prove that the function has at most a certain number of zeros. And if the two bounds agree, we're done. For example, consider the function g defined by the equation g of x equals x to the 6 plus x squared plus x minus 2. How many zeros does it have? First, I will use the intermediate value theorem. This should be familiar. I already presented a similar example when I introduced the IVT. The function g is a polynomial, so it is continuous on all the reals. I can plug in a few values and I notice that g of minus 2 is positive, g of 0 is negative, and g of 1 is positive. A continuous function that switches from positive to positive must have at least two zeros. By the intermediate value theorem, there must be at least one zero between minus 2 and 0, and there must be at least one zero between 0 and 1. But are there more? The IVT can never answer this. It can only tell us that there are at least a certain number of zeros. Rolle's theorem will help us with the rest. Let's pause the example for a moment and think more generally. Consider a function f. Assume for simplicity that f is continuous and differentiable everywhere. Now, assume f has two zeros, x1 and x2. Then I can use Rolle's theorem for the function f on the interval x1, x2, because the value of f at the endpoints of the interval is the same. Rolle's theorem says that the derivative f prime must have a zero between x1 and x2. We have drawn an important conclusion. Between any two zeros of the function, there must be at least one zero of the derivative. Now let's take it one step further. Assume f has three zeros instead, x1 smaller than x2 smaller than x3. Then there must exist a zero of the derivative between x1 and x2, and another one between x2 and x3. Similarly, if f has four zeros, then the derivative must have at least three zeros, one between each pair of consecutive zeros of f. We have drawn a second important conclusion. The derivative f prime must have at least as many zeros as the function f minus 1. Or equivalently, the number of zeros of the function is at most the number of zeros of its derivative plus 1. This is just the same inequality. This is important enough that I am going to call it a theorem. And the only hypothesis we had assumed was that f must be continuous and differentiable on an interval. And this is exactly what I needed. I now have a way to say that the number of zeros of a function is at most something. Let's go back to the original example and see if we can finish it. Remember, I was trying to estimate the number of zeros of this polynomial. I already knew it had at least two zeros. Now I would like to prove it has at most two zeros. The theorem I obtain suggests that I look at its derivative. The derivative is g prime of x equals 6x to the 5 plus 2x plus 1. And I don't know how many zeros g prime has. But look instead at the second derivative. The second derivative at x equals 30x to the 4th plus 2. Aha! x to the fourth is always non-negative. So the second derivative is always strictly positive. So the second derivative has no zeros. How does this help me? The theorem I just proved said the number of zeros of a function is at most the number of zeros of its derivative plus 1. Let's use it on g prime as a function. The number of zeros of g prime is at most the number of zeros of its derivative g second plus 1. That is 0 plus 1, which is 1. And now let's use the theorem again on g as the function. The number of zeros of g is at most the number of zeros of its derivative g prime plus 1, which is less than or equal to 1 plus 1, which is 2. Perfect. To summarize, the IVT says this function has at least 2 zeros. Rolle's theorem says it has at most 2 zeros, so it has exactly 2 zeros.